Okay, welcome everyone. So today we're going to continue the topic of Markov decision processes. And today we're going to be talking about pretty much the last topic, which is called the policy methods. So we have already talked about the model and example, and we've talked about the grid world example, which is a maze-like problem. The agent lives in a grid matrix, n by m, and the walls block the agent's path. There's some noisy movement. Sometimes tries to go this way, ends up this way. There's a certain discount for the rewards. It can get a living reward, or it can get a bigger reward at the end. And that's all defined in your overall grid world definition, the MDP definition. We have already talked about what are the optimal quantities, the V star and the Q star values. The V star values that represent the value of a state. Q star values represent the value of in one state taking an action and thereafter continuing to do the optimal operations. We talked about the policy. Okay. And all of the values V star and Q star have to take into account the discount rate, etc. So those are the optimal quantities we have already talked about. And again, given a certain grid world with a certain noisy settings like 0.8, 0.1, 0.1, and a gamma of 0.9, you can achieve a V star value calculation and arrive at these values. If this part is not clear, then please watch some of the previous videos where we have already talked about this one. Similarly, the Q star values represent the values for each state and the action pair. So in this case, because we consider 4 actions, we have for each state 4 actions, and therefore 4 Q star values. Okay. Today, though, we're going to be talking about something fairly different, and these are called the policy methods. Within policy methods, we have 3 key topics to understand. Let's make sure we understand all 3 of them. One part is called the policy evaluation, which means that you compute the Q star and V star values very similar to what we have already done, except for the current policy. So in other words, you're given a policy, you compute the values. That's called policy evaluation. That naming makes sense. The other part is sort of the reverse part here, which is called the policy extraction. Let's suppose you're given the best estimated V and Q values, extract the policy. So there's a policy extraction. Given values, come up with the policy. Then there is the concept of policy iteration, which is essentially the iterated use of evaluation, extraction, until you reach a stable optimal policy. So that means we fix a policy, come up with the values, take those values, come up with a new policy, and keep doing the same thing. So those are the 3 key parts: policy evaluation, policy extraction, policy iteration. Let's dive into all 3 of them here. And before that, we should also try to remember, why are we even doing this? What is the problem with value iteration? We've already talked about value iteration in our previous video. It seems very straightforward, and it is straightforward in the sense that it's easy to explain. We can easily understand how it's working. The formula is relatively straightforward. So that's our observation 0. And this is how it works. It takes a vk plus 1, which is the next iteration, computes that using the given transition rate, the transition probabilities, the reward, the gamma, the discount rate, the current estimated V values, and then taking a summation over all possible states where you might end up at, taking the maximum. That's how you do the value iteration. The problem, though, is that it is pretty slow. It takes S square A time per iteration. Why does it take that long? Well, you have S states, and for each state value, you have to do A times S. This max and summation represent 2 nested loops here. So therefore, it's order S square A per iteration. If we do n iteration, that's n S square A. So in that sense, it can be a little slow. Now, another observation we must make is that the action that gives you max at each state many times doesn't change. Initially, surely it changes quickly, but after some time, even though the values keep iterating little by little, the max doesn't change. The one that's max is still the max. So the action that gives you the max rarely changes. And also sometimes you already have the same policy, but the values are still changing, so you keep spending your time on it. While the policy that you end up with is the same policy that you had maybe 50 moves prior, 50 iterations prior. So that's the main problem we have with value iteration. So for that reason, we do the policy methods, and let's dig into the first one, which is the policy evaluation. Again, we're given a policy, we want to find the values here. So we want to compute the V star and Q star values, but now they'll be in the context of this policy. Therefore, we'll refer to them as not really as V star, Q star, but also as V pi and Q pi, because they correspond to the policy pi. And how would we do that? Well, if we were to use expect a max, which takes the max over all actions, but if we're given one policy, then the tree is simpler. There's only one action per state. Now the tree would not have the correct values, and that's fine, but to compute the tree is simpler. The tree is simpler, and therefore to compute the values are simpler. So this is what the tree looks like if we have to do the optimal action versus we just have to do what the pi says us to do, the policy pi says us to do. So therefore, this is a little simpler tree, and therefore, even if we want to use the value iteration approach, at least we won't really have a max here because there was only one action. Therefore, we'll simply compute V pi s is equal to 1 summation. So in a sense, you have the max loop has gone away. So there's no A times A was the number of actions that you would have to do this computation here. And this is what it would look like. So key observation number one that we make is that this is more efficient. Instead of S square A per iteration, it's just S square per iteration because we have only one action per node because we're given the policy. However, a bigger observation that we need to make, which is the more important one here, even though the first one jumps out at us, the more important observation is that if we don't have the max, actually the Bellman equations are just a linear system of equations over all the Vk values here. So therefore, maybe we don't need to use iterations to calculate values at all. We will still use some form of iteration, but for computing these V pi values, we don't need to use iterations at all. We can use some kind of a linear system solver here, okay? And we will have a couple of videos where we try to do those examples, and please look out for the links for those videos on how exactly we would use a linear equation solver here, okay? But now let's dive into the second part of the policy method, which is called the policy extraction. So in this case, we're given the V star values. How should we compute the optimal policy? Now, we want to make sure that we don't think this problem is trivial. It's not difficult, but it's also not super trivial. So it is not just that you look at the maximum V star and go in that direction. That's not the action. Rather, you have to take the maximum action, which gives you take the action which gives you the maximum value here. So this is basically called policy extraction. You extract the policy that's implied by the values here. So these are the V star values, and then we compute the policy here. An example you can see in the context of 0.89 node. This V star value for this neighboring node is 0.98. This one is 0.9. This is the wall, and yet the pi that we come up with is this one. So this is not super trivial. You have to do it correctly by doing this argmax. Okay. Now, if you're not given V star values, but you're given Q star values, then you actually have a super trivial case. Then you simply take, okay, which one is the maximum one? As you can see, for the same vertex here, for the same cell, this Q star value gives you 0.76, 0.7, 0.89, so therefore you take 0.89. So if the Q star values are given, then the actions are super trivial. With V star values, they're possible. You just have to do it correctly. Okay. Now that we have the policy evaluation, policy extraction, we can come to policy iteration. Policy iteration just means that we're going to iterate this in a loop, take the values, compute the values, come up with a new policy again, and keep doing that. So this is an optimal approach. This is an alternative optimal approach for optimal values. That first of all, we compute the utilities for some fixed policy, which can also be a degenerate policy, like everyone goes north. And then once you have the values here, you come up with a new policy extraction, which we can also call the policy improvement, because we will have a new policy here. Well, it's possible you don't get a new policy, you get the same policy, in which case you're done. But at least in the initial stages, you're going to get a new policy. So update the policy using the one-step look ahead like we talked about, and these feature values, and keep repeating them. So keep repeating them until the policy converges, right? So that means that you do this step here, and the new policy is the same exact as the old policy here. So this is called policy iteration. It's still optimal. And in some cases, this can converge much faster compared to value iteration approach. So these policy methods are super useful trick in our arsenal when we want to use when we're dealing with MDPs here. So for that reason, I highly recommend that everybody becomes familiar with what policy methods are. Okay. And again, this is a little bit about the mathematical view of how that is working. So we can use the value iteration for this, or we can use the linear equation one. And then we keep coming up with the improvement. We come with a new policy and keep doing that. Okay. So that's pretty much what I have. The key takeaways, we already knew about value iteration from the previous approach. We're now talking about policy iteration. They're going to compute the same thing. These are all optimal values. In value iteration, you keep the iteration updates a little bit more work. It updates both the values and the policy. So we don't really track the policy, but by taking the max, we are always recomputing it. In policy iteration, we do this in passes. So in each pass, we update the utility with the fixed policy, then we evaluate, then we again do a policy extraction, and then the new policy will either be better, so in which case we have some improvement, or will just simply be done. They both are dynamic programming methods for solving the MDPs, and again, I suggest that you know and be very comfortable with both of them. All right, that's all I have. Look out for some more videos that talk about specific examples of how to use the linear equations here. Okay.